Alright then, so the chapter which we're going to start is intermediate code generation, and this is last but one topic when it comes to the module 5, and few of the important topics is how to convert, or what happens when we have a pass tree or a syntax tree. How exactly will it be converted into machine code, right? So those are the topics which we're going to see today in the class. So coming to the intermediate code generation, this is our this is the phase which comes in the semantics, and in the synthesize model of the compiler, the front end analyzes the source program and creates an intermediate representation from which the backend generates the target code. Okay, so this is relatively towards the other side of the program. This is the backend, as with the parser and analysis, syntax analysis, they all come under the front end. So looking into the block diagram here, parser will give us the pass tree, and static checker will check for whether all the terms are according to the syntax or not. If it is proper, then the intermediate code, which is neither belonging to the static checker or not towards the code generator, it generates the intermediate code or the representation which is helpful for the generation of code generator. So local structure of a compiler front end looks in this way. So till here it's all about the front end, till the intermediate code. On the other hand, it will be a backend. Few things which we need to learn here is the static checking. Parsing is where till now which we have studied, and the static checking includes the type checking. What do we know about the type checking? The data type checking, or whether it is according to the format or not, according to the syntax or not. So ensuring the operators are applied to compatible operands or not. It also includes any syntactic checks that remain after the parsing. Example can be in this way. It assures that a break statement in C enclosed within a while for or a switch statement. Exactly. What's the use of inserting a break statement in looping constructs, right? So if you're putting a break statement in the looping constructs, every time it just comes out for the first go itself. So while is based on the condition, and for is based on the number of iterations, which we already know. And when it comes to the switch case statements, break statements might be necessary, or else it just starts executing most of the cases which it selects. So it will be an error, right? So this is about the syntax checking. The process of translating a program in a given source language into the code for a given target machine is where we look into the code generation, or the considering the operations. The source program will be converted into high-level intermediate representation. We don't need this high-level intermediate representation. We need the low-level intermediate representation, right? So we need to be converting from the high level towards the low level, and from the low level or the intermediate representation we generate the target code. Ultimately, target code is what we are looking for. High level representation are close to the source language and are well suited to tasks like syntactic type checking. So excuse me. So the syntax tree is one way of checking whether the given syntax is proper or not. Right? Previously, we saw that in our shift reduce parsing, or LL of one parsing, that is top to bottom approach. Right? We had a few of the tuples where those tuples were empty. Right? If I encounter any of the cases for those tuples which are empty, that means that there has occurred an error. So syntax tree helps in that way. Low level representation are close towards the target code, right? As we know that target code is nearly with respect to the machine understandable code. This is about the machine code, right? So this is high level code, right, which we write. Most of our programming languages are high level programming languages. So we need to convert it into machine level, right? So an intermediate representation may either be an actual language or it may consist of internal data structure that are shared by phases of compilers. So anyhow, if any program or any cases which we see, it needs to be pushed into all the phases of the compiler, right? So moving on, the variants of syntax tree. Nodes in a syntax tree represent constructs in a source program. The children of a node represent the meaningful components of the construct. So looking into the syntax tree, they are just derived from the parse tree. So parse tree has non-terminals within them. Syntax tree do not have any non-terminals within them, but they have their own structure of where operators and operands. Operators will be the node, and the operands will be their leaf nodes, right? So that was about the syntax tree which we looked previously. From the syntax tree, we also understand that the children of a node represent the meaningful components of a construct. Next comes our DAG, standing for directed acyclic graph. This is another approach or another way of representing the pictorial representation of the graph, right? So here the directed acyclic graph, looking into the example of an expression, a DAG leaves representation, the atomic operands, and interior nodes represents the operators. As I said, leaves are operands, right? So the leaves or the ends will be the operands, and when it comes to the nodes, those will be the operators. For example, plus is the operator, a is the operand, b is also the operand, right? So a plus b, got it? As in the syntax tree, a node n in a DAG has more than one parent if n represents a common sub-expression, but in the syntax tree, the tree for the common sub-expression would be replicated. That means for the tree representation, you can have more such expressions. That means many duplicate expressions as many times as the sub-expression appears in the original expression. But in our DAG, we avoid it. We don't want n type of sub-expressions to be repeated. We should have only one copy of each expression to be, right? So looking into one example, we try to understand what DAG representation actually states. DAG gives the compiler important clues regarding the generation of efficient code to evaluate the expression, right? So things to be looking through this case here is, you need important clues of efficient code to be evaluated with the expression, right? We want the code to be efficient as possible. Looking into the DAG here, you'll try to understand what exactly is the things happening here, right? For the expression a plus a star within brackets b minus c plus again within brackets b minus c into d. What you can see here is I have few of the operands which are repeating twice. So b and b is repeating here, c and c is also repeating here, a again it is repeating, d is of only one form, right? So I have a DAG which here states that with not more sub-expressions we need to prepare. So not more sub-expressions refers to I cannot have a duplicate entries. So I should have only one copy within my graph, right? So here, as I said, first identify which are the operators and which are the operands. So which are the operators? I have plus as operator, 1, then star, then minus, star, minus, again I have plus, minus, star. If you can recollect this expression here, so I have a and a which is repeating, right? So here if I go with this operator here, operator's left child is a and operator's right child also finds a in it, right? So we need to start in such a way that I have only one copy of each and every expression. So once you look into it, b minus c and b minus c is common here, right? So and it's also the half nearly. So this b minus c is the left child of the operator plus, and this b minus c is the right child of the operator. First thing, you identify which will be my root, right? So this plus can be the root, so write down the root. So once you write down the root, this complete thing comes on the left side and this complete thing comes on the right side. So the case is I have star plus operators on my left child and star towards the right child, which it can see. Anyhow, minus is also one operator which it can see, but star and plus are the major which this root can see into, or this node can actually see into. So here this plus left is this complete expression, leaving this as it's a common expression, it sees this plus. So plus is viewing another plus. So plus is viewing another plus. Left child of this plus is a. So left child of this is a. What about the right side of this plus? It sees a and star. Okay, star is the right child here. So plus right child is star. Again, who is the left child of this star? Left child of this star is a. As I said, according to the algorithm, I need to first find out the expressions before itself, right? Do I already have that particular expression? Yes, I do have the expression. So as star's left child is a, star's left child is a, and star's right child is, with respect to the operator, it is minus. So I come to the other side, minus is the right child. Left child of minus is b, right child of minus is c. So this becomes b and this becomes c. Again, on the other side, I have plus on my main node. The right child of this plus is star, right? So here my operators can repeat, no issue with that, but operands should not repeat. So I have star as my right child here. So star will be the right child for plus, and the left child of star is minus. So left child of star is minus, right child of star is what? D. So this is a DAG representation which you can see. I hope I have made the topic clear for you. If you have any doubts, can you let me know in the comments. So here the expression goes in this way. How did I construct this DAG? The leaf for A has two parents because A appears twice in the expression. As we all know, in the expression A plus A star, A has been repeating twice. The second occurrence of the common sub-expression B minus C are represented by one node, the node labeled as minus. So that's about the expression here. Further looking on towards the SDD to the produce DAG. So I have a production E tending to E plus T, minus T, T, E, T tending to E, ID and none, right? So looking into the example for this, E tending to E plus T, E tending to E plus T, E minus T, and E tends to T. T tends to E, T tends to ID, E, T tends to none. So here these I have to write it in semantic rules, right? STD is where you represent in the semantic rules. So E dot node is equals to E1 dot node. So here the plus is the operator, the plus is the node, left child of plus is epsilon, I mean E1, and the right child is T. Basically this E and E1 both are same. In order to differentiate between them, I have made it as E1. You can use any remark like star or any other thing. So E dot node is equals to my new node, which is plus, left child is E1 and the right child is T. So next is E tending to E minus T. So E dot node is equals to new node of minus, left child of minus is E1 dot node and the right child is T1 dot node. The other case is E tends to T. Here E dot node is equals to T dot node. So T dot node is equals to E dot node. T dot node is, this is a new leaf again. This plus minus were operators. So this is my identifier. So it's a leaf. So T dot node is equals to new leaf of ID, comma, it's an entry, ID entry. Similar to that, T dot node is equals to new leaf, which is num, and the value for this is num value. It will construct a DAG before creating a new node. These functions first check. Alright, whatever the functions which it might give, this is the case, or this is how the procedure looks, how the value will be pushed towards the top end, right? So initially we started with the leaf and we move towards the node, right? Let me draw the case here or the DAG and we'll try to understand. So I had plus here, plus left child was A, plus left child was plus again, and I have A, so left child of plus was A, right child of plus was star, and left child of star is again A, right child of star was minus, and I have B, and I have C, right? And on the other case, right child of plus was star, and left child of this star was B minus C, and the right child of star was D. Let me check out. So it's the same case, I guess. So plus star B minus C, and it was D, right? So here, this is the conversion. This is the operation where I'm converting into the first expression, right? A first expression via the DAG. So here the first thing is I should start with the leaf. So A plus A. So my first term is A. So this will be my P1. This will be the step P1. So again I have another entry for A plus A, right? So A cannot add itself. No, A cannot be worked out with a single operator. We need two operands per operator. So P1 itself is A. P2 is also A, where P1 is equals to P2. The next case is P1, P2, it sees plus. So this P3 will be the value with respect to the leaf ID of B, right? So B will be my P3 and C will be my P4. First filling out with the values. So minus will be the new node. So minus will be, the left child of minus will be P3 and the right child of minus will be P4. So this will be, of course, P5. So here I have a star here, right? So the star here is P1 and P5. Left child of star is P1 and P5. So this is gonna be P6. Plus left child is P1 and right child is P6. So this will be P7. Next case, left child of this star is P5, and before going to it, I have another case of B minus C, right? So this B is again taken with the entry. So this is 8, which is equal to P3. This is the case. So this is a new expression with the b, which you can call, and it will be a case of P8. P8 is again a new entry of ID, and P8 is exactly as equal as P3. So similarly, on the other hand, C is having P4, and again it's an ID entry, so this will be my P9. So P9 is equals to P4. This will be P5 will also be again with the same term, will be equal to P10. So P10, the left entry of this is again a leaf, right? So D will be P11. P11 will be the leaf, and the left child of star is P5 and the right child is P11, and this becomes P12. So the left child of this plus is P7 and the right child is 12, and this will be our final node, which is of P. Sorry, this is P13. So P13, left child was P7 and the right child is 1. So when all this is how exactly we looked into, and this is just an explanation of the terms. So looking into one example of DAG here, the DAG for I equal to I plus 10. So what is that you see within this example? We see I have identifier which is I, and I have equal to, and I have another identifier. Then I found out that I have an operator 10, and I have a number which is 10. So I have 4 different values which I will be looking into, right? So all these things will be saved in the sort of an array with the content of a array. So within the array I have ID, num, plus, and equal to. So ID, anyhow, it's the entry of I, which whatever the entry of I which I provide will be saved. And for num, it is 10, so the 10 will be given here. Then followed by, I have a next important operator which is plus. Plus left child is, what is the left child of plus? It is I. What is the right child of this value? It is num. So getting the index of 1. Yes. So for the second case of the right child, getting the value from num. That's what the index 1 and 2 will be, the left child and the right child for this case. Followed by I have equal to's left child is I. So it has its reference here. So the right is complete term of I plus 10. I plus 10 is actually this plus, right? So I plus 10, that is 1 plus 2. This plus will be referred, that is index 3 will be referred. DAG to write this I equal to I plus 10. Remember that I cannot use many expressions, so I need to reuse the particular expressions. So I have considered equal to, left child of equal to is I, right child of equal to is plus. It's a node. So again plus left child is I. So I'll rephrase it in this way. So right child of 10 is, right child of plus is a num value which is 10. I hope I made the topic clear here. That's about the DAG representation, and this is basically the explanation of how it works. The algorithm is pretty simple. This is what you need to look into in the first place. To construct the nodes of a DAG using the value number method, you always need to get the operator, left child, and the right child. So L is the left child and R is the right child. And what will be the output? The output will be the signature with respect to the operand left child and the right child. First thing is search for the particular value within your array if it is already there. So search the array from the node M. The M will be your table with the label operand, left child with L and right child with R. If there is such a node, return the value of M. If you already have an entry of A, return the value of this a, or here it is I, return the value of I. If not, create a new entry for the new node in the array with a label where giving the left child and the right child, and return its value number. Value number in the sense it will be the index number. The above algorithm yields the desired output by searching the entire array every time, and which puts it where the nodes are put into the bucket, each of which has few nodes, and yeah. So, and delete the elements of the set and to determine whether a given element is currently in the set. So to construct this we need to generate the hash table, and hash table looks in this way, right? So I have few elements within an array. So let's start with the index 0, and it goes on till some n, right, 20, and it goes on. So array of buckets headed with index by hash values, right? Basically this has with the value, right? So here it goes on. As I said, with the algorithm, check into that particular table M, go and check whether you already have that particular value present in the array or not. If it is present, get the value, get the hash value, right? So get the value and create its particular node, where this node is also looking for the particular entry which is already present, because I don't want this node to be again inserted and making duplicate nodes. Just refer to the same nodes. Getting? So if in case it is not there in the particular table, create another entry in the end, for which a new entry will be made for the left and right, and return the value. So an array indexed by hash value holds the bucket headers, each of which points to the first cell of the list within the linked list of a bucket. Each cell holds the value number of one of the nodes that hash to that bucket. So that is node operator left right can be found on the list where header is at the index, header of operator left and right of the array. So ultimately we move towards the top. So we'll look into one particular example problem for this. So constructing a DAG for an expression. So I have expression x plus y, x minus of x plus y into x minus y, plus x plus y into x minus y. Many stuffs are repeating here, right? So identify which will be my header node on the top, right? So we say that the case of plus will be within the node, because this complete term within the brackets, it's within the brackets. So this will be under the left child, and this will be under the right child. So left child's, if I consider this as a header, so I start with a plus. Plus, this is bracket here, and I have minus, and this is the other thing. So plus left child is minus. So first go with the plus, and plus left child is minus. What is the plus right child is? Star. Plus right child is star. Okay, first let's deal with the left hand side. It sees left is minus and x plus y, and again on the right hand side it sees the minus sees star on the right hand side. So minus is seeing star on the right hand side. Why I am going to look into the star is this x plus y is same again here, this x minus y is again same here. So it is both common terms which we can work out now. So minus left child is plus. So minus left child is plus, and plus left child is x. So now you can write this left child of plus is x, and the right child of plus is y. Then minus is what we dealt about here. Right child of this is star, right? So this minus right child is star. So this is where we looked into, and this star is again having the left child as plus and the right child as minus. So left child as plus and the right child as minus. Here if I go here, it will be in a loop, so try to avoid. So with the operators you can create more number of values, right? You can have more number of it. So here plus, this plus, left child is x, which I already have, and right child is y, and this minus, left child is x, so it is referring to the x value, and right child is y, and the right child is y. By default this is already been done, because this star is the right child of plus, this star is right child of plus, and left child of star is plus, left child of star is plus, and right child of star is minus. And similarly x plus y, x is having reference to x plus y, minus is having reference to x and y. So this will be your DAG representation for the expression which you look here. Then we'll look into few small example programs of DAG, and here a plus b plus within brackets a plus b, so this can be the left child, right? So left child of plus is again plus, right child is also plus, so plus is my header, and as it sees left child also plus and right child is also plus, fine. But for this left child, what is a, left child is a, right child is b, so a and b. But here again for this plus was also it is a and b, so this will be your DAG for the expression a plus b plus within brackets a plus b, right? If you look into this particular expression pretty closer, if you take off this bracket, it's all about a plus b plus a plus b, right? So here, how to write the array for this? What are the things which you see? I see two identifiers, which is a and which is b. Make the table ready with a and b. Then you see 1 plus, right? So 1 plus is for getting the value of this a plus b, and 1 plus is the value itself of a plus b, right? So this is how it is. So first ID is a, second ID is b. So for the first plus, it is at the leaf, right? So 1 will be referred here for the child, and 2 will be referred for the right child. Similarly, for this plus, the third itself, because this value and this value it needs to consider. So here for this plus, for the top one, right? So this was 1, this was 2, and this was 3. So this plus is seeing this 3 from the left side also, and also this it's seeing 3 from the right side also. Basically it is 3 expression which you see on left side plus the 3 which it sees from the right side. Get it? So what does it have in the 3 as? It is plus. So this is what will be referred to the left child as well as to the right child. So this will be the array representation of it. Similarly, take this as an homework, a plus b plus a plus 6. Work it out yourself, right? Take a screenshot of this if you want. Try to work out with this, where a plus b plus a plus b is what, pretty simple, where I have considered this left child is this, right child is this, and you can work out with it. So take this particular example also and try it out as an example and construct the table. So basically I have only 2 operators here, a and a, right? Ultimately many plus I have. So how many pluses you have? These are the number of pluses, how much you have within the cases. Okay, so try to solve that, and that will help you a lot.